Okay, let's talk about rate of reaction. This refers to how quickly reactants are consumed and products are formed. So we're talking about changes in time. We can quantify it by looking at a change in concentration over time. So the concentration of the reactants will decrease over time, and the concentration of the products will increase over the time. The rates that they change at are also related to the stoichiometry of the reaction as well. Okay? So, our average rate of our reaction is delta C, I'm talking about the change in concentration there, divided by delta T, the change in time. Okay, so here I'm going to model, we've got A plus B, so A is my orange circle, B is my pink circle, they're coming together to form C, which is actually this one, but I'm going to represent it by squares to make it really distinguished. And so I've got a model of it here, a model of my reaction, and I'm also going to graph the concentration of these over time, okay? And we're just going to step through and see what happens. So I've got a lot of A and B, so they're up here on my graph, and I've got 0C, so I've just put it, I know it's a little bit above the 0 thing there, but we just wanted to see it, so I've got it starting there, okay? And I'm just going to step through in little steps of time and see what happens, okay? So here, we've just let the reaction go for this little amount of time, okay? And you can see that over that little amount of time, a lot of changes happened. You can see a lot of green has formed, so therefore up here, and the amount of pink and orange has gone down a lot, so down here. So there's been a lot of change in a little bit of time, okay? And that happens because there's a lot of possible collisions that could have happened between the reactants in that time, okay? There was a lot of orange and there was a lot of pink there to react. There was a lot of collisions that were successful, and so a lot of the green product had formed. Let's take another step forward in time, okay? Now we're up to here. Okay, and you can see that more green has formed and we've lost a bit more orange and pink, but not at the same rate. It's slowed down somewhat. You can see that in my rough curve here that I've just used straight lines, that the gradient has dropped for each of them. So it's been roughly the same amount of time again in the second step, but we've slowed down the reaction, and the reaction has slowed down because if you look at the model here, you've got more greens blocking the way from orange meeting pink. We've got more products getting in the way of the reactants from forming, okay? So the reactant concentration is going down and the products are slightly in the way of it. So the reaction slows down because there's less likely successful collisions because of those conditions. Okay, let's take a step forward again. Roughly the same amount of time again, and you can see the reaction has slowed down a little bit more as well, because again we're forming more green, so it's blocking the way, and also there's less orange and pink to meet each other successfully. So it's getting harder and harder to form the product because the reactants are finding it harder and harder to find each other. Okay, let's go another few steps as well, and look, the reaction is nearly all the way there. It's slowing down because pink and orange are finding it harder to find each other and have a successful collision. So the reaction is slowing down, slowing down. It's still going. It hasn't completely ceased. There's still in my model there, one pink and one orange. Oh, look, and I've taken it all the way. So I've converted all the way over to everything being green and orange and pink being 0. Okay, so notice we get not a straight line, even though I've kind of dot to dotted it, which I don't like, but we've formed two curves. Okay, a steep curve at the start and then it shallows out over time. And for the product, a steep curve and it shallows out over the top. Okay, notice that the amount of product that I formed is the same concentration of the reactants that were there, and the reactants dropped at the same rate as well. and that we'll get to soon relates to the stoichiometry of a 1a going plus 1b going to 1c, okay? If you change that stoichiometry, you're going to change the graph as well, okay? So, for concentration versus time graphs, the reactants should decrease over time. The product should increase over time, and the gradient of the slope is dependent on many factors, okay? And these can be changed, and we'll talk about changing these factors of the reaction later, but one cannot, and that's the stoichiometry, okay? Here I've got an example, and it is slightly different in that it's not following it goes to 0 and all the way, but let's have a look at the stoichiometry in this reaction. I've got nitrogen gas meeting 3 hydrogen gases and forming 2 ammonias, okay? So we've got a 1 to 3 in the reactants to 2 products, okay? You can see that here the reactants are dropping. We've got the hydrogen in green there dropping, and we've got the nitrogen in blue there dropping. But notice that the drop in the blue is not as much as the drop in the hydrogen, okay? Or you can think of the steepness of the curve. The steepness of the hydrogen curve is 3 times the steepness of the nitrogen curve there. It's showing the stoichiometry of the reaction. And the red product there, the ammonia, is increasing, but notice that the curve is roughly, it's the opposite, but it's roughly 2 times the drop of nitrogen, but flipped around, mirrored, okay? So the concentration will change in set stoichiometric ratios, okay? So think about the shapes of those curves and the stoichiometry. That will never change, but we can change the overall steepness of the curves by reaction conditions, okay? But let's do some examples to finish this little bit off. So nice and simple, I've got A in aqueous going to B in aqueous. Okay, and here's my graph here. My reactant A has started up here and gone down to 0, and my product B has started at 0 and gone up to here. Okay, calculate the average rate of reaction for B. Okay, so we need the change in concentration of B over the change in time. So the change in concentration for B will be the final concentration of B, which is 1.700 moles per liter, minus the initial concentration of B. Oh, have I got this around the right way? Yeah, final minus initial. Yeah, that's okay. Which is 0.00 moles per liter, divided by the final time, which is 500 seconds, minus the initial time, which is 0 seconds. So simplify that, and we've got 1.00 moles per litre divided by 500 seconds. And I'll get my calculator, and I'll get my answer in moles per litre per second. Okay? And notice it's a positive sign here. It's increased. Okay? So 1.7 divided by 500 equals 3.4 times 10 to the negative 3 moles per litre per second, or moles per litre per second. Okay? The average rate for A, okay, so the change in the concentration of A over the change in time equals the final concentration, which is down here, which is 0 moles per litre, minus the initial, which is 1.7 moles per litre, okay, over the final time, 500 seconds minus the initial time. Okay, notice the similarity here, okay? It's just the same, but negative. Negative 3.4 times 10 to the negative 3 moles per litre per second. All right. That works out nice and good because we had a stoichiometry 1-to-1. Okay, for the reaction, A plus 3B going to 2C, how does the rate of disappearance of B compare to the rate of production of C? Okay, so the change in B compare to the change in C over time. Okay, so you can see that for every 3 B's that are lost, you're producing 2 C's. So the rate of disappearance of B is 3/2 the rate of appearance of C. Okay, 3/2 the rate of appearance of C. There we go. All right, so it's B for this one. Okay, for the synthesis of ammonia, what we were talking about earlier, it's found that at a certain time, the rate of reaction for ammonia was positive 0.1 moles per litre per second. What is the rate of reaction for nitrogen in this instant? Okay, so, so the rate of change in concentration of nitrogen over time is going to equal the rate of change of the concentration of ammonia, over time, times it by the molar ratio. Okay, all right, let's get it around the right way. Ammonia and nitrogen are at the top. So nitrogen is 1, ammonia is 2, so it's going to equal half that. Okay, so, but it's going to be minus, isn't it? Okay. It's going to be a minus in there because it's disappearing. Okay, so let me get rid of that positive. That's going to be a negative 0.10 moles per litre per second divided by 2 or times it by a half, which equals 0.05 moles per litre per second. So negative 0.05 moles per litre per second. What is the rate of reaction for hydrogen? So the change in hydrogen, change in time, equals what we know, change in ammonia over time, times it by, and we'll put the negative there, the change in, what do we want? Hydrogen over ammonia. Okay, and what's in front of the hydrogen? 3. And what's in front of this? So it's going to be 3/2. So negative 3 on 2 times it by the positive 0.10 moles per litre per second. Negative 3/2. Oh, I can do that. That's negative 0.15 moles per litre per second. All right. Hopefully those examples have helped you out. You can now do this worksheet. Okay, thanks guys.